Welcome to this lecture on the diversity of chordates. Today, we are going to explore one of the most fascinating evolutionary marvels in the aquatic world, the swimbladder in fishes. Have you ever wondered how a fish can hover perfectly still in the middle of a lake without sinking to the bottom or floating to the top? By the end of this video, you will understand the brilliant biological engineering and the fundamental physics that make this effortless hovering possible. Let us dive right in. To begin our journey, imagine you are swimming in a deep pool. If you want to float perfectly still in the middle of the water, you will quickly realize it is quite difficult. If you hold your breath, you slowly float up, and if you exhale completely, you sink like a stone. Scuba divers solve this exact problem by wearing a special vest called a buoyancy compensator, which they inflate or deflate with air from their tanks. Fishes have been using this exact same brilliant engineering trick for millions of years. Instead of a vest, they possess a built-in balloon-like organ inside their bodies. By filling this organ with gas, they achieve perfect weightlessness in the water. Now that we understand the basic idea of this internal balloon, let us look at its formal biological definition. The swimbladder, which is also known as a gas bladder, is a specialized, thin-walled sac found in most bony fishes, belonging to the class Osteichthyes. If you look inside the fish, this organ is typically positioned in the dorsal portion of the body cavity. It sits snugly just below the vertebral column and directly above the digestive tract. Developmentally, this organ is fascinating because it arises as an outpocketing of the embryonic gut tube. Because of this specific developmental origin, the swimbladder shares a very close evolutionary relationship with the lungs found in terrestrial vertebrates, like us. Building on that developmental connection to the gut, it is important to note that not all swimbladders remain connected to it in adult fishes. Depending on the specific species, we see two main anatomical conditions. In the physostomus condition, the swimbladder remains connected to the gut by a small tube called the pneumatic duct, allowing the fish to gulp air from the surface. In contrast, the physoclistus condition means the swimbladder is completely closed off, and the fish must secrete gas directly from its blood into the bladder. Regardless of the type, by regulating the exact amount of gas inside this internal sac, the fish can precisely control its overall body density relative to the surrounding water. Understanding these anatomical types leads us to ask why this organ is so crucial for survival. The primary and most critical function of the swimbladder is to provide neutral buoyancy. This means the fish does not have to expend precious muscular energy just to keep from sinking. Without it, a bony fish would be significantly heavier than water because bone and muscle are very dense tissues. They would be forced to swim constantly just to stay afloat, much like a shark must do. Beyond buoyancy, the swimbladder serves other amazing functions. It can act as a resonating chamber to produce or amplify sound for mating calls, and in some primitive fishes, it even functions as an accessory breathing organ to extract oxygen in stagnant waters. To truly visualize everything we have discussed so far, let us look at this anatomical diagram of a bony fish. Notice how the large, light blue swimbladder is perfectly positioned in the upper half of the body cavity. You can see it sits right below the segmented vertebral column, which provides structural support, and right above the coiled digestive tract. This central location is vital because it keeps the fish's center of gravity stable, preventing it from rolling over. In the top right inset, you can also see the specialized blood vessels and the gas gland, which work together to add or remove gas from the bladder. This visual confirms how perfectly integrated this organ is into the fish's anatomy. Now that we have seen the anatomy, we must look at the physics that makes this organ work. The upward force that keeps the fish afloat is governed by Archimedes' principle, which we can express with this fundamental equation. Conceptually, this formula tells us that the upward push on the fish is exactly equal to the weight of the water it pushes out of the way. Let us break down the symbols. F sub b is the buoyant force pushing upward, measured in newtons. The Greek letter rho represents the density of the surrounding water. V stands for the total volume of water displaced by the fish, which includes its inflated swim bladder. Finally, G is the acceleration due to gravity. If the fish increases its volume V by inflating the bladder, the upward buoyant force increases, causing the fish to rise. Before we dive into the mathematical proof of how we find the required volume, let us see this principle in action with a concrete example. Imagine a bony fish that has a total mass of 2 kilograms swimming in freshwater with a density of 1,000 kilograms per cubic meter. The fish wants to rest completely motionless to hide from a predator. To find the exact volume needed for this neutral buoyancy, we divide the mass of the fish by the density of the water. Plugging in our numbers, we divide 2.0 by 1,000. This gives us a final volume of 0.002 cubic meters, which is exactly 2 liters. Physically, this means the fish must adjust its swim bladder so its total body volume is exactly 2 liters to hover effortlessly. Now that we have successfully calculated the required volume, let us understand exactly where that simple volume formula came from. This chunk of our derivation sets up the physical conditions for neutral buoyancy. For a fish to hover perfectly still, the upward buoyant force must perfectly balance the downward gravitational force, meaning the net force is 0. The downward force is simply the weight of the fish, which is its mass times gravity. The upward force, as we just learned from Archimedes, is the water density times the fish's volume times gravity. By setting these two opposing forces equal to each other, we create an algebraic equation that perfectly describes the state of hovering. Continuing from our balanced force equation, we can now solve for the unknown volume. Notice that the acceleration due to gravity appears on both sides of the equal sign. Because it is a common factor pulling on both the fish and the water equally, we can cancel it out completely. This leaves us with the mass of the fish equal to the density of the water times the volume. To isolate the volume, we simply divide the mass by the water density. This final mathematical result proves that the required volume for neutral buoyancy is directly proportional to the mass of the fish and inversely proportional to the water density. This is exactly the formula we used in our previous example. This understanding of volume leads us to an important environmental challenge. What happens when the fish changes its depth? Gases are highly compressible, meaning their volume changes drastically when the surrounding pressure changes. We model this behavior using Boyle's law. Conceptually, this law states that for a fixed amount of gas at a constant temperature, the pressure multiplied by the volume remains constant. In our formula, P1 and V1 represent the initial pressure and volume of the swim bladder. P2 and V2 represent the final pressure and volume at a new depth. Because they are inversely proportional, if the fish dives deeper and the pressure goes up, the volume of the swim bladder must go down proportionally. Let us apply Boyle's law to a real scenario before we look at the algebraic rearrangement. Imagine a fish swimming near the surface where the pressure is 1 atmosphere and its swim bladder has a volume of 100 milliliters. Suddenly, it dives to a depth where the pressure doubles to 2 atmospheres. We need to find the new volume. Using our rearranged formula, we multiply the initial pressure of 1 by the initial volume of 100 and then divide by the new pressure of 2. This gives us a final answer of 50 milliliters. Physically, this means the increased water pressure has crushed the swim bladder to exactly half its original size, which will make the fish sink faster unless it actively adds more gas. Now that we have seen the dramatic effect of pressure in our example, let us quickly prove how we isolated that final volume mathematically. We start with the standard form of Boyle's law, where the initial pressure times volume equals the final pressure times volume. Since we want to find the new volume at the deeper depth, our goal is to isolate V2. To do this, we divide both sides of the equation by the final pressure, P2. The P2 terms on the right side cancel out completely. This leaves us with our final result. The new volume is equal to the initial pressure times the initial volume, all divided by the new pressure. This simple algebra is what allowed us to calculate the crushed swim bladder volume. We have covered a lot of ground today, so let us summarize the most important ideas. First, the swim bladder is a remarkable evolutionary adaptation, an internal gas-filled sac that acts as a built-in buoyancy compensator for bony fishes. Second, by providing neutral buoyancy, it saves the fish immense amounts of energy that would otherwise be spent fighting gravity. Third, we saw how fundamental physics governs biology. Archimedes' principle determines the exact volume needed to float, while Boyle's law explains why changing depths compresses the bladder. You now understand both the anatomy and the physics of how fishes conquer the three-dimensional aquatic environment. Great job following along with these complex concepts.